came up with a theory that explains almost everything about life on Earth. So where is the blunder? So the blunder had to do with heredity. At Darwin's time, Darwin didn't know any genetics. And we cannot blame him for that because nobody knew any genetics at the time. So Darwin adopted the theory of heredity that was the prevailing theory at the time, which was that of blending heredity, which means the characteristics of the mother and the father get blended in the offspring just like you would mix paints. Okay? Now, again, this is not a blunder because he didn't know any better. This was the best theory available. So he adopted that. That's not a blunder. The blunder was in not understanding that if this were the correct theory of heredity, natural selection could never have worked at all. And let me explain that. Okay? Suppose you have a population of 1 billion butterflies, and they are all white. And there is one which is black. And suppose that it is being black, that's the characteristic that gives an advantage, both in terms of coping with the environment and all that, and in terms of producing offspring. Okay? According to Darwin's theory of evolution by means of natural selection, this would have meant that after many, many generations, the entire population of butterflies should turn black. Now, what happens under blending heredity? The black butterfly would mate with a white butterfly. They would produce a gray butterfly. That's, you mix like paints. Okay? Notice, black has disappeared from the population, never to return again. In fact, the gray butterfly would mate with another white butterfly, and it would produce an even paler shade of gray butterfly. Very quickly, you will have more than 50 shades of gray. But you will never see black again. You will never see black again in this population. So this was a serious, serious problem, which Darwin at first did not recognize, and it was pointed out to him by an engineer, Fleming Jenkins, who wrote a review of Darwin's book. Now, it is true that Darwin did not catch this thing, but we have lots of evidence that Darwin was unhappy with blending heredity. He didn't know how to correct it, but he was unhappy with it. First, let's see what is the difference between blending heredity and Mendelian heredity. You know, that's named after Gregor Mendel. That's the theory of heredity that we actually talk about. Let me first just say in simple terms, what Mendelian heredity is telling us is that it's not like fusing paints. It is more like shuffling cards. If you have cards, and let's say you have a jack, and having a jack is good, it doesn't matter how much you shuffle, you would still have the jack. That's the key point, okay? Unlike with paints. So here is what happens in blending heredity. In blending heredity, let's say that capital A gives you the color black, lowercase a gives you the color white, and you get from one parent the black, from the other parent, let's say, the white. Together they produce gray, that's fine. But here is the main point in blending heredity. The capital A and lowercase a cease to exist. They blend together to form something which I called A1 here, which is gray, and that's it. From now on, you will never have black. What happens in Mendelian heredity? You know, Mendel did these experiments with peas, yellow peas, green peas. He found the ratio of 3 to 1. From that, he concluded these laws. And that's how it works. You get capital A, lowercase a. They are black and white. They produce gray. In this theory as well, gray. However, the capital A and the lowercase a continue to exist individually. And now you have two parents. One gives you capital A, lowercase a. The other one gives you capital A, lowercase a. And then depending of how you combine them, you can get black, gray, or white. And if black indeed gives you the advantage, then over many, many generations, the whole thing will turn black. That's the thing, right? Not like in blending. You know, in blending, you know, somebody gave you a gin and tonic, they will keep pouring tonic into it. At the end, you will not feel the gin. I mean, that's how it goes, right? So, this is the situation. Okay. Now, I told you that Darwin was unhappy with blending heredity. How do we know that? Already in 1857, this was 2 years before he published On the Origin of Species, he wrote that he believes that propagation by true fertilization will turn out to be some sort of mixing and not true fusion. More like cards, not like paints. And then in 1866, he wrote to Wallace, you know, his friend and competitor at some level. He wrote something that you read this today and you say, how is it possible that nobody thought about that before? He said, look, every female of the world produces a distinct male and a distinct female, and not some intermediate hermaphrodite. So it cannot be that it is blending, you know? So he understood that blending cannot be right. He just didn't know how to correct it. And in fact, his attempt to correct it went completely the wrong way. So even though he's on the horse here, he didn't find the correct theory. Now, there are no fewer than 4 books that will tell you that when Darwin wrote this in 1866,
Roman Murray, who's a postdoc in Edinburgh now. That are soft matter. Polymers, micelles, suspensions, emulsions, foams, liquid crystals, and this may or may not mean much to you. These are the things that we encounter daily. So, an example of a polymer solution is an engine oil, so that consists of long polymer chains in a short molecular solvent. Micellar systems, which are also polymer-like structures made out of soap molecules, are in nearly all brands of shampoo. And suspensions are toothpaste suspension, etc. I can go on down this list. So you can see why these are called soft matter. They're mostly pretty soft. But there's also a whole branch of physics connected with the kind of high-tech end of soft matter. So where I was until last year. Are soft matter. Polymers, micelles, suspensions, emulsions, foams, liquid crystals, and this may or may not mean much to you, but in fact, these are things that we encounter daily. So, an example of a polymer solution is an engine oil, so that consists of long polymer chains in a short molecular solvent. Micellar systems, which are also polymer-like structures made out of soap molecules, are in nearly all brands of shampoo. And suspensions are toothpaste suspension, etc. I can go on down this list. So you can see why these are called soft matter. They're mostly pretty soft. But there's also a whole branch of physics connected with the kind of high-tech end of soft matter. So all polymers, all plastics rather, in processing go through a molten stage or a semi-solid stage. Additives very similar to what you have in shampoo are used in things like this oil pipeline down here. Pharmaceuticals, drug delivery, etc. Foams, foams get used in cleaning up after fires and things like that. And liquid crystals are in every single one of your laptops and mobile phones. So, the picture as physicists we can have of these systems is to back off from the molecular detail of exactly what's in there and try to classify them into broad categories. And then within each category we're hoping to find universe, which does include the phenomena I'll show you later in the jar. So polymers we think of as molecular spaghetti. Suspensions, or these kind of dense suspensions here, are basically molecular ping-pong balls or microscopic ping-pong balls. In a solvent such as water. Liquid crystals are also like that. There's needle-shaped structures here. So today I'll focus on suspensions, the baseline model, molecular ping-pong balls, and how this structure, the fact that I have some kind of organization of these solid particles inside my suspension, how does that control its macroscopic behavior, and in particular, how does it control flow behavior, which, as we shall see, can at times be spectacular. So one of the main intriguing features of the flow behavior that we'll see is the presence of an effect like a traffic jam. It's a jamming phenomenon. And so what I want to do next is show you some other natural phenomena involving jamming and unjamming. So the top right is fairly familiar. Bottom left is